Okay, so today we're going to discuss the experiments performed for Lab 8. So let's switch to the tablet view for that. So we're going to be looking at Lab number 8, which focuses on the gas laws. So in experiment 1, we are trying to figure out the percentage of hydrogen peroxide in a solution of hydrogen peroxide, which is 3%, which is quote unquote 3% by mass on the bottle. So the way that we're going to do that is hydrogen peroxide can decompose to yield hydrogen gas and to yield water and oxygen gas. And this oxygen gas we can collect and measure the volume. So as we've seen in our classic setup, we have a graduated cylinder with an initial volume of air and a volume of water. We have a tube and it's immersed in a beaker. And that tube is connected to a reaction flask. And in our reaction flask, we have 5 milliliters on what we measured to be 5.1 grams of hydrogen peroxide solution. And we have yeast, which serves as the catalyst for this reaction. A catalyst is defined as a species that is neither produced nor consumed in a reaction that accelerates the rate of reaction. So it makes it so instead of the decomposition of hydrogen peroxide taking days, it takes mere seconds to minutes. Okay, so after our reaction proceeds, we are going to end up with a final setup where our water level has dropped substantially. So now we have a new volume of oxygen plus air and a new volume of water at the end of our reaction. So from this, we can figure out the volume of oxygen by taking our final volume minus our initial volume. In this case, we measured our final volume experimentally to be about 99.5 milliliters, and our initial volume was 5.0 milliliters to give us a volume of 94.5 milliliters of oxygen. This is data that we've collected from our lab recording. Does this make sense so far? Does this make sense so far? Okay, so now what we're going to do is the ideal gas law states that the pressure and volume of a gas is equal to N, which is the moles of gas, times R, which is a constant, which is 0.08206 liter atmosphere per mole Kelvin, times the temperature in Kelvin, where Kelvin is equal to degrees Celsius plus 273.15. So P is the pressure. We need the pressure in atmospheres, and V is the volume in liters. Okay, so we know our volume is 94.5 milliliters. So we can convert that to liters because we know they're 10 to the negative third liter per mil. So that in turn gives us 0.0945 liters. Okay. The pressure, we're going to look up the local barometric pressure, and we're going to assume that the pressure inside, the pressure of our gas is about equal to the barometric pressure. Okay, so let's look that up. So for our local barometric pressure, let's see. We have 758.2 millimeters of mercury. And to convert, we know that 1 atmosphere is equal to 760 millimeters of mercury. So our pressure, in this case, our atmospheric pressure, which is approximately equal to the pressure of our oxygen, it's about 0.9976, which yep, perfect, atmospheres. Okay, what temperature did we measure for our water? What was the temperature of our water, which is about the same as the temperature of our oxygen? What was the temperature of our water? What was the temperature of our water? 20.6 degrees Celsius, yeah. Okay, so then we take our 20.6 degrees Celsius, we add 273.15, and that gives us 293.75 Kelvin. Okay, so now we can solve and we can say the moles of oxygen are equal to PV over RT, where we take the pressure, which is 0.9976 atmospheres, times the volume, which is 0.0945 liters, over R, which is a constant, which is 0.08206 liter atmosphere per mole Kelvin, times the temperature, which is 293.75 kelvins. Atmospheres cancel, liters cancel, kelvins cancel. And if we punch this into our calculator, the moles of oxygen are equal to 0.00391 moles of oxygen. We retain 3 sig figs because our volume has 3 sig figs. Now we did make some assumptions here. We neglected the pressure of water vapor, which is approximately 17 millimeters of mercury. You can redo the calculations, but in the lab book, they don't account for the pressure of water vapor, so it's not a requirement. If you'd want more details into how to account for the pressure of water vapor, what you'd do is you'd look up the pressure of water vapor in a table, which is you get about 17 millimeters of mercury. And if you wanted to know the pressure of O2 adjusted, we just take our 758.2 minus 17, which would give us 746.2. However, if you carried this through your entire calculations, you'd get a value if you performed it using the adjusted method, which is I'm not requiring you to do. The NO2, which is adjusted, would be 0.00384 moles. So this is a difference of about 1%. So it's not going to make a huge difference in this case. At higher temperatures, it plays a bigger role. So just showing that there is a way to account for the fact that we have some water vapor collected, but considering that we're using a graduated cylinder, the uncertainty in the graduated cylinder is probably going to be greater than this correction factor. Okay, with that aside out of the way, does everyone see how we calculated the moles of oxygen using the ideal gas law and how we calculated each of our components that we needed, how we got the volume, pressure, and temperature? Does this make sense to everyone so far?
Yes.
Okay, perfect.
For the just to keep it like nice and clean on the post lab, do you want us to put the work right there or like on a separate sheet of paper?
However you want to do it, as long as it's all submitted.
Okay.
So now that we have the moles of oxygen, now the reason why I had you measure the mass of hydrogen peroxide is because we're going to use that to calculate the mass percent. So the mass percent of hydrogen peroxide is equal to the grams of hydrogen peroxide over the grams of our solution times 100%. Okay? So to calculate the grams of hydrogen peroxide, we're going to need to look at our chemical equation now. And again, we have another very nice student-friendly chemical equation in that if we start with 0.00391 moles of O2, how many moles of hydrogen peroxide are present? Let's see. How many moles of hydrogen peroxide react per mole of O2 generated? What's our mole to mole ratio? What are our reaction coefficients in this case? 2 to 1, exactly right. We have 2 moles of hydrogen peroxide per 1 mole of oxygen. The moles of oxygen cancels, and we're left with, at the end of our calculation, so we have 0.00391 times 2. That gives us 0.00782 moles of hydrogen peroxide. Now, from this, we can figure out the grams of hydrogen peroxide. And the way that we do that is we just take our moles, which is 0.00782 moles of hydrogen peroxide times the molar mass. And how many grams are in a mole of hydrogen peroxide? What is our molar mass in this case? What is our molar mass of hydrogen peroxide? So for H2O2, we have 16 times 2 plus 1 times 2, which gives us 34. So we have 34 grams per mole. We punch that into our calculator. We get 0.26588 grams. We're going to carry through this number. If you wanted to report a truncated value, it would be 0.266 grams of hydrogen peroxide. So now, if we want to calculate the mass percent of hydrogen peroxide, we're going to take the grams of hydrogen peroxide over the grams of our solution. So we take 0.26588 grams over 5.1 grams of solution times 100%. And that gives us a calculated value of 5.21 or 5.2% for mass percent. So not the most accurate method. If we double check our bottle, we see it should be around 3%. But this method has a few sources of air. It's likely we ended up collecting a little bit of extra gas from the gas trapped in our tubing. Let me just check to see. So everything looks good from here. If we wanted to calculate a percent air, we'd take the literature value, which is 3%, minus our experimental value over the literature value, times 100%. And that in turn gives us a percent air of about 73%. So not the most accurate determination. But then again, the setup we were using, if we had a more accurate method of measuring the volume, and if we had a way to purge any of the gas remaining in our graduated cylinder, we probably would have an easier time getting accurate volume readings for our sample. So that's an overview of the experiment to determine the percentage of hydrogen peroxide in a solution. Let's just check to make sure everything pans out. Yep, everything looks good. Okay, so that concludes our overview of the calculations for part 1 of this experiment